Welcome to this presentation on locally decodable Slepian-Wolf compression. My name is Shashank Watadka and I'm with IIT Hyderabad. This is joint work with Aslan Chamkirtan, who is at Telecom Paris, and Venkat Chandar, who is with DE Shaw. Firstly, I'd like to thank the organizers for allowing me to present this virtually, and I apologize for not being there in person. Let me start. We're all familiar with the problem of classical lossless compression, which is now well studied, and we have efficient entropy achieving compression algorithms such as LIMP-LZIP. These algorithms were designed for archival purposes. The main goal was to save space. However, our needs today are changing. We are generating vast amounts of data. In particular, data sets in genomics, astronomy, and machine learning can occupy several terabytes, if not petabytes of space. One main feature of these data sets is that there's a lot of redundancy in them. Therefore, they're highly compressible. Since space is expensive, we want to compress these data sets. On the other hand, if we use traditional compressors such as LIMP-LZIP, then we run into a problem. We're not interested in just storing these data sets. We also want to continuously interact and process these data sets. If we use a traditional compressor such as LIMP-LZIP, then every time we want to read or write or search through this data, we have to decompress the entire data set, which is wasteful. So the need of the hour is to design schemes which allow us to compress data and process data directly in the compressed domain. This is exactly what this talk is about. Our goal is to design distributed compression algorithms for correlated sources, which does the following. We can achieve rate tuples in the Slepian-Wolf rate region. At the same time, if we want to recover just one source symbol, we should be able to do so without decompressing everything. In particular, we want to make sure that if we want to recover the ith source symbol, then we should be able to do so by probing a very small number of compressed bits. This is what we call compression with random access or compression with local decodability constraints. Let us quickly recall the problem of distributed compression of correlated sources. This is also called the Slepian-Wolf problem, and here we have two source sequences, or it can be generalized to multiple sources. But for now, we'll assume that there are two source sequences, xn and yn, which have IID components, but for each I, xi and yi are jointly distributed according to some known distribution pxy. Xn is encoded into a binary code word of length nr1, let's call it cnr1, and yn is independently encoded into a binary code word of length nr2, let's call it cnr2. A decoder who has access to both CNR1 and CNR2 should be able to recover both xn and yn with an arbitrarily low probability of error. So the goal is to design these encoders and decoders such that the rates R1 and R2 are as small as possible and the probability of error is vanishing in n. This problem was solved by Slepian and Wolf, who showed that for any R1, R2 which satisfies the following three inequalities, it is possible to construct encoders and decoders operating at rates R1 and R2 for which the probability of error decays exponentially in n. On the other hand, if R1 and R2 don't satisfy these constraints, then it is impossible to construct encoders, decoders for which the probability of error even vanishes with n. Our problem is the following. So we have correlated sources xn and yn as before. Xn is encoded to an nr1 length code word, let's call it C. Yn is independently compressed to give an nr2 length binary code word, let's call it C prime. But now at the receiver, we want to be able to recover just xi-yi pairs, individual pairs, by probing only a subset of these compressed bits. In particular, we want to design what is called a local decoder, which is an algorithm that takes an index I between 1 and n as input and outputs an estimate xi hat yi hat. Now the local decoder for every particular I which is given as input probes a very small number of compressed bits. So for example, suppose we want to recover only x2, y2. Then the local decoder is fed the input I equal to 2, and based on this, the local decoder decides to probe a small number of compressed bits. In this example, it probes C2, C4, C3 prime and C4 prime and outputs x2 hat, y2 hat. Maybe if we want to recover x3, y3, then the local decoder now probes C2, C3, C1 prime, C2 prime and outputs an estimate of x3, y3. So one point to note here is that the encoders don't know which I will be requested at the local decoder. So we want to compress in such a way that every xi, yi can be recovered from the compressed sequences, but which locations to probe depends on the I specified at the local decoder. So for each I, there's a set of locations that the local decoder probes, and this is denoted I subscript I. So in this toy example, in order to recover x3, y3, we have I3 is equal to 2, 3, which is the second and third bit of the first sequence, and 1 prime, 2 prime, which is the first and second locations of the second sequence. Now, the performance of the local decoder is measured using what I call the local decodability, which is the maximum number of compressed bits that need to be probed in order to recover any particular source symbol. The probability of local decoding error is the probability that xi hat yi hat is not equal to xi yi. So the goal of this problem is to design encoder 1, encoder 2 and the local decoder jointly such that R1 is as small as possible, R2 is as small as possible, the local decodability is as small as possible, and the probability of local decoding error is also as small as possible. Now here's a simple solution for the local decoding problem. Now instead of compressing xn and yn directly using a Slepian-Wolf scheme, we do the following. We partition each of the source sequences of length n into chunks of b symbols each. So xn is partitioned into chunks of b symbols each, yn is partitioned into chunks of b symbols each, and each chunk is independently compressed using a standard Slepian-Wolf compressor. Now the decoder, if it wants to recover one symbol, all it has to do is decompress only the corresponding chunks. So the local decoder, which is just a standard Slepian-Wolf decoder, reads only the chunk which includes the symbol that we're interested in. So it reads these two chunks and outputs an estimate. So what is the local decodability? The total number of bits that we need to probe is just BR1 plus BR2. So the local decodability grows linearly in B. And what is the probability of error? The probability of error is the probability that the corresponding chunk is decoded incorrectly, and this decays exponentially in the block length B. Overall, we can achieve any R1, R2 in the Slepian-Wolf rate region, and the probability of local decoding error decays exponentially in B, or in other words, it is exponential in the local decodability. Therefore, there is this trade-off between the local decoding error probability and the local decodability. If we want a constant local decodability, then the probability of error can only be a constant. If we want a vanishing in probability of local decoding error, then we have to make sure that the local decodability also grows with n as n tends to infinity. The question that we want to answer is that, can we do better? Is it possible to get a better trade-off between the probability of local decoding error and the local decodability? Now let us see what is achievable for single source compression. The single source compression with random access was studied in a sequence of works. Essentially, the problem is to design a fixed length compression scheme for memoryless sources whose rate is close to entropy, and once again the local decodability and the probability of error are defined in an identical fashion. So in this setting, it was shown by Mazumdar et al. That there exists a locally decodable compression scheme achieving a rate close to the entropy. The local decodability scales as a constant independent of n, and the probability of local decoding error decays exponentially in n. Now this is much better than the baseline scheme that I had just mentioned. So now the trade-off is not exponential. We can achieve constant local decodability and vanishing in n probability of error. This is a phenomena that we call the strong locality property. What we want to find out is it possible to achieve strong locality for Slepian-Wolf compression? That is, can we design a compression algorithm for which the local decodability is a constant and the probability of error decays as n tends to infinity? So if R1 and R2 are both greater than the respective entropies, then it's simple to achieve this. You just use the single source scheme for xn and yn. Our main contribution is to show that if R1 is less than the entropy or R2 is less than the entropy h of y, then it is impossible to obtain strong locality. This holds for a very large class of sources. We say that a joint distribution is X confusable if for every distinct X and X prime, there is at least one symbol Y which confuses X and X prime. In other words, the probability of X comma Y is greater than 0 and the probability of X prime comma Y is greater than 0. Now, just by definition, any joint distribution with full support is X confusable. It is also Y confusable. But it is possible to find confusable sources which don't have full support. And here is an example. So let us assume that X is drawn Bernoulli half and Y is obtained by passing X through a BECP. Now this is X confusable but not Y confusable. To see why, note that the erasure symbol confuses X equal to 0 and X equal to 1. The probability of 0 comma E and the probability of 1 comma E are both greater than 0. On the other hand, it is not Y confusable because Y equal to 0 and Y equal to 1 cannot be confused. Our main result is the following. If we consider Slepian-Wolf compression of any X confusable joint distribution Pxy and we compress Xn at a rate below its entropy, then the probability of local decoding error is always lower bounded by 2 to the negative constant times the local decodability. In other words, the baseline scheme is optimal. On the other hand, if Pxy is not X confusable, then you can find an R1 and R2 for which R1 is less than h of x, R2 is equal to h of y, and strong locality can be achieved. In fact, for confusable distributions, we have an even stronger result. If R1 is less than h of x, then any local decoder which is allowed to probe D-lock bits of the compressed version of Xn and has complete and free access to Yn still has the probability of local decoding error bounded from below by 2 to the negative constant times the local decodability. So to show this, we essentially need to lower bound on the probability of error of the following problem, where Xn is compressed to CNR for R less than h of x, and the decoder has to estimate Xi from a D-lock number of compressed bits of Xn and the entire Yn. And the probability of error of this is lower bounded by the probability of error of the hypothesis test, which has to distinguish between Xi equal to X star and Xi is not equal to X star for any X star. The first step of the proof is essentially to look at a lower bound on the probability of error of the hypothesis test, assuming that the decoder has access only to the compressed bits of Xn. In this case, just using the source coding theorem, we can show that this is lower bounded by some constant times 2 to the negative D-lock. What we want to then show is that the probability of error of the hypothesis test is lower bounded by 2 to the negative constant times D-lock even when the decoder has access to the whole of Yn. Now, to handle general X confusable distributions, we identify a coupling, essentially a random variable X tilde, such that X, Y, X tilde forms a Markov chain and Px given Y equal to Px tilde given Y. Now, such a distribution has the property that Px x tilde has full support, and we can show that the probability of error of the hypothesis test is lower bounded by the probability that Xi equal to X star, Xi tilde equal to not equal to X star, and both Xn and X tilde n are such that they agree in the compressed locally probed bits. Since Px x tilde have full support, we can find positive constants beta and gamma which depends only on Px x tilde, such that the following holds. So to put things together, the probability of error of local decodability is lower bounded by the probability of error of the hypothesis test, which is consequently lower bounded by this probability in terms of the coupling, and this is lower bounded by the probability of in terms of x raised to beta times the probability in terms of x tilde raised to the gamma, and therefore the overall probability of local decoding error is lower bounded by 2 to the negative some constant times the local decodability, and this completes the proof. So essentially what we've shown is that the baseline scheme is optimal in terms of the local decoding error probability. However, there's a problem with the baseline scheme, and that is once we fix a B, that is once we encode, there is no way of achieving a smaller local decoding error probability even if we are later willing to read more bits of the compressed sequence. In order to remedy this, we designed a new scheme which does the following. It achieves any rate pair in the Slepian-Wolf region, and now the local decoder takes as input not just the index corresponding to the symbol required, but also the target probability of local decoding error. Depending on the value of eta specified at the local decoder, it probes a certain number of bits, which is polynomial in log 1 over eta, and outputs an estimate whose probability of error is at most eta. So this summarizes the results in our paper. For more details, please go through our conference paper. We also have a longer version upon archive where we have more general proofs and all the technical details. So with this, I'd like to conclude. Thank you for your attention.